Hello, and welcome to Lecture 5 on the topic of current and Ohm's law. This is Lecture 5 of Electricity and Magnetism and is building on ideas that we've seen so far, namely defining charge, electric field, and voltage. Okay, now we've also defined capacitance already. We'll not relate capacitance to resistance at this point, okay? Which is going to be one of the main things we talk about here. Of course, the other, as the name implies, as far as main topics, current, okay? All right, so building on many ideas, especially the concept of voltage and charge. We want to become familiar with the concept of electrical current and its units, understand the difference between electrical current and electrical drift speed, very different, learn how voltage and current are measured, realize that Ohm's law is a proportionality law between current and voltage and defines resistance. So it's actually the definition of resistance, we can say accurately, comes from Ohm's law. We want to distinguish between resistance and resistivity. Okay, they sound very similar, but you'll see they're quite different quantities. And see the similarities between how resistance and capacitance are determined by physical parameters. So I said we're not really talking about capacitors. It's true, we're not going to have any problems that relate capacitors to resistors or Ohm's law, or current for that matter. But we are going to show that there's a kind of a similar idea there about how we can find the physical parameters for each. Okay, so let's go ahead and jump right into defining current. Okay, so current is flow of charge per time. So flow of charge per time. Okay, now the units, I will say it's a base unit. So units are amperes. Okay, and that's an A, and it's equal to a coulomb per second. The ampere is the base unit of all of electricity and magnetism. So it's the base unit of E, that's electricity, and something we'll talk about later, M for magnetism. Okay, so really it is the fundamental base unit. Its dimensions are just current because it is the base unit, so it is the base dimension. Okay. Okay. Dimensions are just the letter I for current. And the last thing I want to say is that it points parallel to the electric field, okay? Which is well, anti-parallel to the direction that an electron would experience a force, okay? So we'll point out that the current points parallel to the electric field vector and opposite, as in 180 degrees opposite, to the force experienced by an electron. Because as we know, the electric field points one way, the force experienced by an electron points exactly the opposite way. And so current is consistent with electric field, which makes sense. We should stick to one rule here. So if electric field, the force felt on a positive test charge, that's the direction that a positive charge would move. Current points in that direction. That means that current points in the direction that positive charge would move. Now that is a little weird though, right? It's consistent, but it's weird from the get-go because as we talk about wires and we talk about current through metal wires, the charge carriers, the things that are actually carrying charge that are moving through the wire, certainly are not positive charges. They're electrons. So that means that we'll always have this thing to remember that the actual electron motion is one way and current is exactly the opposite way. Okay? Now, on top of that, there's another important concept that we want to differentiate from current, and that's the actual electron drift speed. And this represents the average velocity the average velocity of electrons in a metal. So the average velocity of electrons in a metal. In a metal, and to be specific, when subject to an electric field. Now, the electric field here is a uniform, constant electric field, the type that would continue to push all the electrons in the same direction, okay? That's the type of electric field we generally talk about here, okay? So definitely one unchanging electric field is then going to cause electrons to move. And the reason that it's called the drift speed is because actual electron drift speed is greatly limited. You could think reduced by the many collisions between electrons. So the many collisions between electrons and between electrons with atoms. Between electrons and between electrons and atomic nuclei. Okay? Because that's what's happening is the actual electrons get bounced around a lot. They're all going to experience a force that is exactly anti-parallel to the electric field. So there's a uniformity there in terms of where they feel a force, but then, of course, when they knock into something, then we have a conservation of momentum situation, which means they could bounce back the other way. So overall, they're going to drift. They will slowly make their way in one direction, but it's slow because they have to bounce around and ricochet off of each other and other obstructions on the way of getting pulled opposite the electric field, okay? And it really is a dramatically smaller number than the actual, say, speed of the electric field. Okay, but we'll run those numbers in one of the examples, okay? I also want to define a multimeter. I think that's a good chance to do that. It's a tool used to measure voltage, current, or resistance. You might think more have to do with labs, but these are all concepts we talked about, so it's good to have the application of them. So tool used to measure voltage, current, and resistance. Okay? So I bring this up because voltage, we talked about that. We talked about voltage changes. Voltage, after all, is potential energy divided by charge. Potential energy normalized by charge. That's voltage, okay? Well, so then if we're measuring voltage, we measure voltage across something. So voltage is measured across a circuit element, and it is measured in parallel. So voltage is measured across a circuit element and is measured in parallel because it's the difference. It's literally looking at two elevations, okay, to use an analogy, okay, like two potential energy elevations between something. You measure on one side, you measure on the other, you calculate the difference. That's the voltage. Okay, that's why it's across. If you don't recall what a circuit element is, we've only talked about one so far, but a circuit element is a capacitor or a resistor, okay, or a battery, and finally, in later chapters, or an inductor. And there are more examples, but they're beyond the scope of the class. So far, we have talked about one, though, the capacitor. So if you want to review the idea of voltage across something, look at the lecture, rewatch, view the lecture on capacitance and capacitors, and you'll see how we discuss voltage there, okay? Now, brand new idea, current is measured through a circuit element, okay? And as such, is measured, you guessed it, in series, okay? Okay, so this has some interesting applications. I think you have to kind of see it yourself, but if you're working with something that's in parallel, that means that you would add your multimeter, After all, that's what we're talking about here. You would add your multimeter to your situation, to your circuit element, to your circuit, whatever it may be. You add it in to the side, okay? But if you're adding a multimeter in series, that means you have to actually open up your circuit somehow, disconnect wires, and add that extra thing in a row, okay? So it requires a more invasive technique to use the multimeter to measure current, okay? But multimeters do measure both voltage and current, and then they can calculate resistance. Okay, and we'll talk about that because that's going to lead us right to Ohm's law in just a couple of moments. Okay, all right, and as far as this idea of being in series or in parallel, the quick summary there is parallel is side by side, series is in a row. If you want to review those topics and what they look like, then look at capacitors in the previous lecture. Okay, so on to Ohm's law. What is Ohm's law? I said we're going to have to understand it as a proportionality law. What does that mean? Okay. So it is the proportionality law that defines resistance. And physicists like to talk about proportionality laws. Everyday people don't know what the heck we're talking about. Essentially, it just means it's a law that forces us to define a new quantity. In this case, the quantity we're defining is resistance. Proportionality law that defines resistance. Okay? So we saw before that capacitance, if you recall, a good necessary comparison here, capacitance was charge per volt. This was the definition of capacitance. It's not how we find capacitance for a particular capacitor for the circuit element, but it's the definition of capacitance, okay? Here, the proportionality was capacitance, none other. That was the capacitance. Okay, that was the proportionality. Now that formula, C equals Q over V, it doesn't have a special name. It's not called, it's not named after anybody. It's not called someone's law. It could be. There's no reason it isn't. But the so-called Ohm's law is an equation just like that just happens to have a name named after a scientist, in this case, Ohm. Okay? Now, what it states is that current is directly proportional to voltage. Okay? So it states that current is directly proportional to voltage. That should make sense based on your understanding of voltage as being an elevation difference. If you have a bigger elevation difference, you can have more flow, right? Makes sense, right? If we're thinking maybe flowing down a mountain, you have a bigger elevation difference, you can have more water flow down that mountain, okay? So intuitively, that should make some sense. It also states that current is inversely proportional to resistance. And as such, it defines resistance. Because that's what really in resistance is. It's some quantity that chokes current, that slows down current. Inversely proportional to resistance. To use the water and elevation analogy, resistance would be rapids. It would be something that's taking away energy from the actual gravitational energy becoming kinetic energy of the stream flowing down the mountain and turning some of that energy into heat, because that's what rapids do. Okay? All right, that's the idea here. Okay? That we have some resistance that's choking the flow of charge. Okay. Another idea, if we're talking about kind of all these the relationships between voltage and resistance and now current, well, we have an EMF. Now this is a strange term, okay, but it refers to the voltage of a battery. So it refers to the voltage of a battery, okay? EMF is measured in volts. So it doesn't just refer to the voltage of the battery, it is the voltage of the battery. It's just another name. It's a synonym for voltage of a battery. So I could refer to the EMF of 6 volts for a battery, or I could say it's a 6-volt battery. those would be interchangeable statements, okay? The letters stand for electromotive force, but we of course know that volts, because after all, EMF is measured in volts, volts are joules per coulomb. Well, last time I checked, joules per coulomb and newtons are not equivalent units, so the electromotive force is not a force at all. It's a term, basically the term is historical baggage. It's been around longer than people have realized that volts are not a force, okay? Next up, we have resistance, okay? So this is the proportionality between current and voltage, okay? That's really what it is. It's proportionality between current and voltage, okay? It has units of, well, volts per amp. Okay, so we'll write it like this. It has units of ohms. That's the term. It has a special name for them. They're represented by uppercase omega, and they are the volt per coulomb. Okay? So, excuse me, the volt per amp. All right, well, then we could rewrite that. Okay, so we know then that we have the joule per coulomb, okay? And then we also have, for the amp, we have the coulomb per second. Okay, see? And so then when we cross multiply here, what we're going to have then is the joule per second. Okay? Joules per second being our units of resistance. All right. Well, what else I want to say about resistance is that it represents a lack of ideal performance in the flow of electrons. It represents the fact that electrons bump into the sides of a conductor like a wire. It represents the fact that some energy is lost from a purely potential energy of the electric field and changed to some other form, like more chaotic energy, like heat. And that's really one of the things that resistors do, is they convert electrical potential energy into heat. They're energy converters. They convert electrical potential energy, just charge times volts, into heat, okay? All right. Now, how is this different than resistivity, okay? Well, resistivity, unlike resistance, isn't a proportionality between fundamental quantities, but instead is a material-specific property. So it's a material-specific property that refers to how much a particular type of material will resist the flow of charge. To a material's ability to resist the flow of charge. And flow of charge is what? Current. Okay, coulomb, yeah, current. Okay. Coulomb per second, the current. So What would have a higher resistivity? A conductor or an insulator? An insulator. Insulators have very high resistivity because they have that material property, though, to almost completely stop electrons from moving. Really good insulators will almost only even allow for any current to flow if they're brought up to really high temperature. Otherwise, they essentially completely stop the flow. Okay, so you can have that sudden change. Okay, but the less ability to conduct means the greater the resistivity. And again, it's a material property. Okay. And actually, I need to get one more line in here for you. And the units of resistivity are resistance times length. So they're resistance times length, which is going to be meters. Okay, length measured in meters. So actually units, omega for ohms times meters. They're ohm meters. Resistivity is measured in ohm meters. Okay? Finally, we have the resistor itself. This is our circuit element for the lecture. All right. A circuit element that creates resistance. All right, so it's a circuit element that creates resistance. All right, and so this is the second circuit element that we have seen. The first, of course, was a conductor. All right, and the circuit element is represented by the symbol. And we'll see plenty of these in circuits to come. They are the most common circuit element. A capacitor, I guess, being probably a more distant third. I guess a battery source, a voltage source, being a close second. But really, resistors, such an important thing, element of a circuit. Okay, so represented as like so. All right, that would be an example of a resistor, and usually the letter R. Well, really always the letter R, but then we can have subscripts to denote whether it's resistor 1 or resistor 2, and we'll deal with situations we'll have more than one resistor. Things to come with resistors is we'll actually start seeing circuits, not in this lecture, but soon, a circuit being a closed loop of wire with some current in it, and we're going to start seeing resistors in parallel and series with each other, very much like we saw capacitors in parallel and series to each other, but with a different set of rules that apply to resistors. But those are things to come. We'll worry about those later. For now, let's just get into working with our definitions of resistors and resistivity that are appropriate for this lecture. All right, which leads us to our key formulas. Okay, so our first key formula here is really just a definition of current. Okay, so there's current measured in amps. Okay, now this would be instantaneous current. I'll go ahead and add that. Instantaneous current, okay? And since it's instantaneous current, it represents the instantaneous rate of change of charge per time. And that's as the amount of time that's actually changing becomes smaller and smaller and smaller. In other words, infinitesimally small, which then leads us to the idea that we have an instantaneous current, okay? And this would be change in charge and elapsed time. Okay, so that's how we define the movement of charge as in charge per second, and the instantaneous rate of change is called the current. Okay, now, the current can also be related to that other quantity I mentioned, electron drift speed. And let's see how. Okay, so I here still represents current. Okay, I is always the letter used for current. So in electricity and magnetism, when you see an I, first thing you just think it's current. N here is going to be the number of charge carriers per volume, often electrons, but not always. Okay, and the reason that we'd introduce something like this is because, after all, if we're going to relate this to the actual drift velocity, which I said is much slower than the current speed, that we're going to, if we're going to do that, we need to find out how many electrons there are in order to bump into each other, because that will make a difference. Okay, so number of charge carriers per volume. Okay, Q is just the actual charge. That would be the charge of each charge carrier. This formula only works if you have a homogeneous population of charge carriers. So in other words, they all have to be electrons, or they all have to be some type of ion. Okay, so this is the charge of individual charge carrier. Okay, for an electron, that would be 1.602 times 10 to the negative 27 coulombs. Okay, this V with the subscript D is the drift velocity. There it is, drift velocity. And that is measured in meters per second, okay, base units. And then A is the cross-sectional area of the path for the electrons. So what that is, it's the cross-sectional area of the conductor, but we can really think of it as the wire, because really most of the time that we're going to be dealing with is going to be the wire, okay? So cross-sectional area of wire. And every time A comes up, it's always going to be the cross-sectional area of the wire. There are some examples, if we deal with an ion fluid flowing through some tube, then in that case, the cross-sectional area would be the tube because it's functioning like a wire. Okay? All right, so there we have the relationship between current and electron drift speed. Next, we're going to get to Ohm's law itself. Okay? So this next formula is none other than Ohm's law. Okay. Ohm's law. Okay, Ohm's law is that law that defines resistance as the ratio of change in voltage over current. All right, looks good. Okay, and looks good. Okay, and then notice we can also replace the voltage as the EMF. So here, this script style of writing E represents EMF. It's a typical way of writing that. And this is EMF as voltage source. Okay, that's what the EMF represents. And of course, I here is still the current, and then R is the resistance. Okay, and here we're always just going to be dealing so far in this lecture with an individual resistor, with an individual resistance. We'll deal with the whole idea of having multiple resistors later on. Okay, so that's our resistance measured in ohms. Okay, all right. So that's how resistance is defined, but that's not how resistance is found. And here's this analogy that I brought up a couple times or hinted at a couple times. How we want to see the similarity between capacitance and the formula that defines capacitance, and then the way we actually find the capacitance of a capacitor, where we need to know the separation gap between the plates. We need to know if there's a dielectric. We need to know if there's, we need to know what the cross-sectional area of the plates are. Well, similarly, with an actual resistor, whether it's just the wire itself acting as a resistor, or if you added something else like a heating element in a tungsten light bulb or an electric heater where you want it to heat up and get hot, right? Or like a heating element in a toaster oven, whatever it may be, that's your resistor. And what you need to know about that resistor is just a couple things. You need to know its resistivity, and you need to know its length and its cross-sectional area, and that's it. Okay, so here rho represents the resistivity. Okay, so this is the resistivity of the wire. I'm going to use the term wire for all these, because imagine a wire acting like a resistor, a wire that's getting hot, like the wire in a toaster, okay, or a blow dryer, okay, hair blow dryer. L is the length of the wire, the total length, okay, length of the wire, okay, and finally A is the cross-sectional area of the wire. Area of wire. Okay, so that's what you need to know. You need to know what material it is, because rho, that's this letter here, the resistivity is material specific, okay, like silver, tungsten, copper, these are all going to have different resistivities. Then you need to know length and the cross-sectional area, okay? And then finally, there's something interesting here, something we didn't see with conductors, but we see a strong temperature dependence, okay? Because it turns out that resistivity really does depend on temperature quite dramatically, okay? And if you heat something up really hot, it's going to allow for the flow of electrons much easier than if it's at, say, room temperature, okay? So that's the formula right here. And let's define a couple of terms in it real fast, and we'll be done with our formulas. Okay, so rho, again, is going to be resistivity. Okay, and I'll go ahead and add, I'll remind you of the units here, that it's going to be, after all, ohm meters. Okay, and you can see how the units work out in the formula to have resistivity defined as ohm meters, because after all, it's an empirical value, right? It's ones that that you just determine through experimentation. There's no way to like determine the resistivity of a material without subjecting it to a test and finding out how much does it stop the flow of electrons. Okay, so here we have resistivity. Okay, then we're going to have resistivity at 20 degrees Celsius. And this is usually the value you look up. If you look up what's the resistivity of copper, you'll find a number, and that's assuming it's at room temperature. Okay, often the table or the web page you found will specify that, but you might miss it. But that's considered the baseline resistivity. Okay, and then as we get colder or warmer from that room temperature, which is assumed to be 20 degrees Celsius, that's where we're going to see the temperature dependence. So this is resistivity at 20 degrees Celsius, okay? This constant right here, this is alpha, is the letter, and what it represents is the coefficient of thermal resistivity, okay? Also often called just the thermal coefficient, okay? So we'll just go ahead and give it that simpler title. So this is the thermal coefficient. And what it's telling us is how sensitive is this material to temperature changes? Does this resistance change a lot per degree Celsius or per Kelvin? Or does it only change a little? Because different materials have different thermal coefficients. They'll all become less resistant. Their resistivity will go down as their temperature goes up. But some change faster than others. Okay, so that's the thermal coefficient. It's another material-specific value. And it has units of inverse Kelvin, which would be the same as inverse degree Celsius. Okay, and then T minus T naught is just the temperature change, okay, from room temperature. Okay, so this is the temperature. It can be negative or positive, usually positive, but temperature change from 20 degrees Celsius, because again, that's the baseline, that's the room temperature. Okay, so here are our equations, we're good to go. You're gonna see that the problems very much involve the equations in a very straightforward way. These are not very complex problems that we're gonna be doing examples for, okay? All right, so type 1, simple problems that involve the definition of current and or electron drift speed. Okay, type 2, simple problems that involve using Ohm's law. So just use this formula, V equals IR. And I say V equals IR because that'd be cross multiplying. V equals IR, right? Okay, so we can do that. Type 3, problems that involve finding the resistance of a resistor of specific parameters. Okay, that can be combined with Ohm's law. So that would be using this formula. The parameters would be length, resistivity, and cross-sectional area. Okay, that's what I mean by parameters, physical parameters. And type 4, problems that involve finding the resistivity of a material and the resistance of a resistor made of that material. Okay, well, if we're finding resistivity, that means it's going to be temperature dependent, because the only thing that resistivity is dependent on is temperature, as far as we're concerned. And so essentially type 4 problems involve using that final equation. So as simple as that. okay? All right, so let's jump into example 1. All right, so if a fluid is composed of ions with 3 missing electrons, and 1.2 times 10 to the 17 of these ions flow through a section of tubing in 1.5 seconds, then what is the average electrical current in this tube? Okay, so the idea there is we're just going to consider I average, okay? And that's just going to be the change in current over the change in time, okay? And in that case, or in this case, it's going to be, well, the change in current is N, that's the number of charge carriers, and then times 3 times the fundamental charge in electron, okay? So then times 3E, okay, all over the elapsed time, okay? Well, we know how many there are. We know there's this 1.2 times 10 to the 17, so some 1,000 trillion of them or something, 100,000 trillion. So 1.2 times 10 to the 17, okay? And that would be charge carriers, but we'll just go ahead and just leave it as a number. And then times 3, and then times the charge per carrier, which is the charge of electron, 1.602 times 10 to the negative 19 coulombs, okay? So that gives us units of coulombs in the numerator. And then our elapsed time is just going to be 1.5 seconds, okay? And then that's going to give us a value of 3.84 times 10 to the negative 2 amps, okay? And that's 38.4 milliamps. 38.4 milliamps. All right, there's our answer. Okay, all right, straightforward enough. Just using some definitions there. Okay, example 2, okay? So a circular wire with a radius of 0.15 millimeters carries a current with a uniform density of 2.8 times 10 to the 7 amps per square meter. What is the current in this wire? Okay, so this one again is using basic definitions. The idea here is that current density, because notice that the current density was defined and the units were given. They were given as current per area. Well, that means that current density divided by area is just current. So it should be as simple as just dividing that current density, be 2.8 times 10 to the 7, so 28 million amps per square meter, divided by our cross-sectional area of our circular wire, so pi r squared. All right, so it'd be pi, and then the radius was given as 0.15 millimeters, which is 1.5 times 10 to the negative 4 meters. Remember to square because it's pi r squared. All right, and so when we work that out, we end up with 40,000 amps. So 4.0 times 10 to the 4 amps. So that's a lot of current, okay? But not unusual. There are millions of amps in certain wires. Okay. All right. So again, another simple definition. Hopefully, all looks good. All right. So let's consider another. Copper contains 8.4 times 10 to the 28 free electrons per cubic meter. Okay. What's that going to be? That's N. Okay. A copper wire of cross-sectional area 7.4 times 10 to the negative 7 square meters carries a current of 1 amp. What is the electron drift speed in this wire? Okay, so how do we go about doing this? Okay, this is part A, so we'll label it as such. All right, so we'll use the formula to relate current and drift speed. So current is N times Q times the drift velocity, or drift speed, times A. Okay, all right, that's good. And then we want to go ahead and solve for the drift velocity. So then the drift velocity, if I'm just going to solve for it, is this going to be the current divided by NQA. Okay, all right. And so let's go ahead and plug in our quantities. Okay, so drift velocity then is going to be 1 amp divided by number of charge carriers per volume, so that would be 8 0.4 is the number we're given, times 10 to the 28. And we'll just write this as electrons per cubic meter, all right? And then we'll multiply by the charge per electron. So that's going to be 1.602 times 10 to the negative 19 coulombs per electron, okay? Makes sense, right? And then I'll multiply by the cross-sectional area, which we don't have to use a formula for because we weren't given the radius in this case, we're just given the cross-sectional area. So it'll just be times 7.4 times 10 to the negative 7 square meters. Okay, and you can see that that's going to give us a final unit of, well, meters per second. See, because we're going to cancel out the coulombs up in the amps. So, and our meters that we're going to remain is going to be in the denominator of the denominator, which means it'll come up to the numerator, and then the seconds left over from our amps will be retained in our final value. So check the units yourself, but that's going to give us 1 times 10 to the negative 4 meters per second. Okay. And then make sure I have space, so I'm going to finish it on this line. Okay, not that we need a lot, but this one requires a couple more lines. So 1.0 times 10 to the negative 4 meters per second. Okay, so that is 1/10 of a millimeter per second. That is really slow. I wasn't kidding when I said that electron drift speeds are really slow. Okay, even though the current we'll see is very fast, the electron drift speeds are not, okay? So let's give an idea about maybe how slow that is. And one way to consider that is what fraction is this speed of the RMS speed of an electron gas at 20 degrees Celsius, okay? So this is a throwback to thermodynamics, specifically the statistical approach to understanding ideal gases. That's often how this subject is described. You can look back on my previous lectures on that very topic. But to find the RMS velocity of an ideal gas, and here we're modeling electrons as an ideal gas, and again, just for argument's sake, just to show how slow the drift speed is, we use the following formula, so VRMS, okay? Not a formula that's given in these notes because it's not appropriate to this new material. This is previous material, okay, but it's equal to the square root, okay, of 3 times the Boltzmann constant times the temperature in Kelvin divided by the mass of the particle. Okay, looks good. Okay, so then, in this case, 3 times the Boltzmann constant, which is 1.38 times 10 to the negative 23 joules per Kelvin, because it has the same units as entropy, because the Boltzmann constant essentially is the constant of entropy, times room temperature in Kelvin, which is 293 Kelvin, and divided by the mass of an electron, which is 9.11 times 10 to the negative 31 kilograms. All right, finish off our square root there. All right, so when we go ahead and figure out that number, all right, then we end up with 1.15 times 10 to the 5 meters per second. So wow, if we make a gas out of electrons, electrons bounce around really fast because they're free to move in all directions. So obviously having an electron confined to a conductor is a big deal. We talk about electrons being free to move within the atoms of a metal, but obviously that freedom is very limited, okay? They can transmit the signal, they're all feeling the electric field, but they sure bump into a lot of things for them to be going that slow. And if we want the fraction, okay, so thus the fraction is going to be our 1.0 times 10 to the negative 4 meters per second divided by 1.15 times 10 to the 5th meters per second. This will just tell us how much slower the electrons are moving in the metal versus as they would be moving as a free gas. Okay, gotta run this number real fast. Okay, and so it's, well, there we go. So 8 point, we'll just do 2 sig figs here, 8.7 times 10 to the negative 10. Okay, so about 1/10 billionth the speed. Wow, So these are slow electrons in our metal wire. But let's make another interesting comparison. And that's, how does this electron drift speed compare not only to the RMS speed of electrons if they're completely free, how does it compare to the actual speed of the electric field? As I say in part C, what fraction of the electric field speed is the drift speed? Okay, well, what is the electric field speed? The velocity of the field, VE. Okay, well, the velocity of the field is the speed of light. The electric field moves at the speed of light. It has a finite speed, but it moves at the speed of light, which is 3 times 10 to the 8 meters per second. Thus, the fraction would be our 1/10 of a millimeter per second divided by the speed of light, which gives us 3.4 times 10 to the negative 13th. So now we have a 10 trillionth, 3 10 trillionths. So the electric field moves incredibly fast. The electrons themselves move very slowly. Okay? Interesting dichotomy there. Okay. All right, now let's move on to a problem here. Oh, yes, that involves kind of dealing with things a bit differently. Just a final take on how we can combine our values here. Okay, so one final definition and one final problem involving the actual drift speed. Okay, all right. So here we have a copper wire of cross-sectional area. Okay, give you cross-sectional area. It carries a current of 126 milliamps. Assuming each copper contributes 2 free electrons to the metal, find the drift speed of the electrons in this wire, and the density of copper is 8.92 grams per cubic centimeter, and its atomic mass is 63.5 atomic mass units. Okay, so how do we go about dealing with this? Well, we need to find the volume of 1 mole of copper. Okay? And that's why I included this one, because it has this different take involving moles, which we haven't seen here. But it definitely, since we are talking about these material-specific quantities, like resistivity and so on, moles may come up. So I wanted to include an example. Okay, so find the volume of 1 mole of copper. Okay, so the volume of the mole is just going to be the mass of the mole divided by the density of copper. Okay. Well, if there's an atomic mass of, so that's the mass per individual atom of copper, 63.5 atomic mass units. Okay, an atomic mass unit is pretty close to the mass of a single proton, right? It's pretty comparable to that. And so we're saying that it has a mass equal to about 63 protons. But it turns out that also means that 1 mole is that many grams. So we can take this and immediately do a conversion in our head and say then, okay, well then the mass of 1 mole, I'll make this clear that as mass of a mole, is 63.5 grams, because that by definition, that's a mole is that much of a substance, okay? And then we'll divide by the density, are 8.92 grams per cubic centimeter. Okay? All right. And then that's going to give us a volume of 7.12 cubic centimeters. Okay? Looks good. All right. Then we're going to convert that over to cubic meters. To convert over to cubic meters, we just divide by 1,000,000. So 7.12 cubic centimeters divided by 1/100 centimeters, because there's of course 100 centimeters per meter, but then we need to cube that. 100 cubed is 1,000,000. So then we end up with 7.12 times 10 to the negative 6 cubic meters. Okay? Then we want to find the number of electrons in that 1 mole of copper, and this is the number of free electrons. We're assuming 2 electrons per atom. Okay? So then, so then we would go over here and find our number of charge carriers, okay? and we're going to find our number per volume. So it's going to be number per volume, just like we would use in the formula for drift speed. Okay, so that's going to be Avogadro's number times 2 divided by the volume. Okay, so it's NA, well, I'll put the 2 in front, and it's only 2 because there's 2 electrons per atom, okay, and then divided by the volume. Okay, so then 2 times 6.02 times 10 to the 23. All right, and that's going to be electrons per mole. So let's say E per mole, and then divided by our 7.12 times 10 to the negative 6. And that's cubic meters, and it's specifically, because it wasn't just any volume, that was the volume per mole, so it's cubic meters per mole. So you can see how moles cancel, and we're just left with number of electrons per cubic meter. Okay, so that should be another one I gotta recalculate. 16, all right, so, or 1.69 times 10 to the 29. So 1.69 times 10 to the 29, and that would be electrons per cubic meter. Looks good. Okay, so now we're finally ready to go ahead and find our drift speed. That was what this was all in service to. So then our drift speed is just going to be our current divided by the number of electrons times the charge per electrons times our cross-sectional area. All right, and now we had to do all that work just to find N. We knew everything else from the get-go. All right, so let's go and plug everything in. So 126 times 10 to the negative 3 amps. We'll have our 1.69 times 10 to the 29 electrons per cubic meter. Our 1.602 times 10 to the negative 16 coulombs per electron. And then finally, our cross-sectional area of 1.24 times 10 to the negative 7 square meters. Clean this up a bit and run our numbers. Okay. All right. It's another one that I hadn't calculated, but so give us a good chance to check all our numbers here. Yeah, 1.69 times 10 to the 29 looks good. Yep, charge per electron. Our small cross-sectional area. It's always really small for wires. Okay. All right, looks good. 10 coulombs. Oh yeah, because we have it's a relatively low amperage. Yep, that makes sense. And then just making sure I didn't leave off a subscript yet. Negative 16. Yeah, 126. Yeah, it's even smaller than I thought it would be. That's why I'm double checking. I got 3.75 times 10 to the negative 8. So really slow. But that's because it is a relatively small. Yeah, it is a quite small current. Okay, well that'll work. So this is our incredibly slow drift speed. 3.75 times 10 to the negative 8 meters per second. Okay, and that's the only time we actually get a velocity is going to be in one like this. Okay, because remember, current is not a velocity; it's charge per second. Okay, but we actually find out how fast they're moving. Well, sometimes they're moving really slow for a small current like this. Okay, all right. Let's take a look at a concept question here. All right, so here our concept question is we have a junction of current carrying wires as shown, and then I give you some values and I ask you to find the one missing value. So the idea here is we just have to make sure that that charge is conserved. Okay, and we'll come back to this in a later chapter, but charge is conserved. Thus, current in equals current out. So whatever flows in has to come out. You can't just destroy charge at the junction, right? Has to come out. Okay, so that means that in this particular junction, I1 plus I2 plus I3 has to equal I4 plus I5. So I1 plus I2 plus I3 has to equal I4 plus I5. Okay, and then we're given some values that we can substitute in. All right, so we know we'll just leave this in terms of I1. All right, and we have that I2 is 3I1. We have that I3 is 5.5 times I2. So with an I2, of course, is 3 times I1, so it'd be 5.5 times 3 I1s. Okay, and then we also have that I4 is 0.75 times I3, which is to say times 5.5 times 3 I1, and then we'll solve for I5. Okay, so we'll go ahead and clean this up. A little bit of simple math here in our concept question. All right, so we'll have a 1 plus 3 plus 5.5 times 3 minus 0.75 times 5.5 times 3. Okay, so 8.125. So I5 equals 8.125 times I1. Okay, and I1, of course, is equal to 2 amps. So, all right, so 16.25 amps. There we go. Okay, from conservation of charge, which tells us the current in equals the current out. Okay, let's do a simple example here with Ohm's law. All right, so this first one, a current of 45.6 milliamps exists in a 220 ohm lamp. What is the applied voltage? Okay, so this one really is as simple as it sounds. We're just going to use V equals IR. Okay, all right, so in this case then, the voltage would be our 45.6 times 10 to the negative 3 amps times 225 ohms. Okay? All right. I think that's going to give us exactly 10 volts, but let's make sure. This number seems really good, but I think that was the idea. All right. Oh, well, it rounds. So if we're dealing with 3 sig figs, it would round to 10.3 volts. There we have it. Okay. So very, very simple, just definition of Ohm's law there. Okay. Not much to do. Okay. Now let's deal with some problems that actually involve resistivity. Okay, so the first one I want to look at is one that has a nichrome wire that is 1 meter long. It has a certain cross-sectional area, and when connected to a potential difference of 2.5 volts, a current is registered. Then I ask for the resistance and then the resistivity. Okay, so for part A, we can forego considering the cross-sectional area and the length. Okay, so for part A, we can simply find the resistance. The resistance is just going to be V over I, of course. Okay, so that's just going to be our 2.5 volts divided by our 4.8 amps. Okay, 2.5 divided by 4.8, so 0.521. So 0.521 ohms. We could also write that as 521 milliohms. Okay, now part B. Okay, well, let's consider. Now we know R, so we can just use it to calculate our next step here, because we know that resistance in terms of the physical parameters of the resistor is the resistivity, rho, okay, and then times the length divided by the cross-sectional area. Okay, so in this case, I want to solve for the resistivity. So if I cross-multiply, that's just going to be the resistance times the cross-sectional area divided by the length. Okay, so then I can go ahead and start plugging values in. So I'll plug in the resistance I solve for in part A. I'll plug in the cross-sectional area. So 1 times 10 to the negative 6 square meters and finally divide by the 1 meter length, which has no numerical effect. Okay? All right, let's see what we get. So times 1 times 10 to the negative 6. All right, yep. So we get 5.21 times 10 to the negative 7 ohm meters. And that is for this particular material, which is nichrome. Okay, 5.21 times 10 to the negative 7 ohm meters. Okay, it's kind of like the friction coefficient. You know how like different materials have different friction coefficients? Different materials have different resistivities. Some just stop the movement of electrons more than others. Okay, now a couple concept questions. So which of the following graphs best represent the current voltage relationship for a device that obeys Ohm's law? Pause the video if you need to, because I want you all to have an answer that you feel confident about. Which one of these graphs for current as a function of voltage, okay, I on the vertical axis, voltage on the horizontal axis, which one represents a device or a circuit element that obeys Ohm's law? Okay, the linear one. Okay, Ohm's law is a linear relationship. So that means that our answer must be B. Okay, all right. Okay, let's look at another concept question, just regards the relationship between cross-sectional area and resistivity. So we have wire 2, this one here, okay, wire 2, is twice the length and twice the diameter, okay, of wire 1, okay. What is the ratio of R2 over R1 of the resistances, okay? So they're made out of the same thing. Now we could change that. We could say that one of them has a resistivity that's twice as much as the other, but here we've kept their resistivity as the same. So we want a ratio of R2 over R1. Okay, so what would that look like, sort of symbolically, right? If we're just using the equations. So R2 over R1, okay, would be rho, all right? And then, well, let's see. The 2 one is the one that's twice as long, all right? So then we'd have 2L up top. Let's going back to this formula here, because it's twice as long. I'm going to use L as the baseline, the length of 1. So it'd be 2L, all right? And then, think about it, it's twice the diameter. Well, if it's twice the diameter, that means it's 4 times the area, okay? And that's simply from the fact that area is proportional to diameter, use d squared. So if you double the diameter, you're quadrupling the cross-sectional area. If you triple the diameter, then your cross-sectional area is 9 times as big. That's where the 4 came from, okay? And then finally for the original one, resistivity, L over A, okay? And so then when we cancel things out, right, just clean this up a little bit, right? Because obviously the resistivities cancel, the L's and A's cancel, and we're just going to be left with a 1/2 over 1. Draw like this, 1/2, right? And then everything in the denominator just becomes 1. So it's just going to be 1/2. The ratio is 1/2. Okay? So if I was to say that, I would say R1 is 2 times more resistant than R2. Is that what you expected? Maybe if the bigger wire would be more resistant, but that's definitely not the case. And we really see it here. That's what's nice about this example, this concept question. So it really highlights how big, long, wide wires are less resistant because they allow the electrons to flow more freely. Narrow wires are higher resistance. All right, so R1 is definitely the higher resistance. R2 is less resistive. Bigger wires are less resistive. Okay, good. All right, let's see. This is our last example. Okay, example 7. Okay, so this one we're doing here is we're just going to deal with some temperature dependence. Okay, so a particular metal has a resistivity of 2.12 times 10 to the negative 8 ohm meters operating at a temperature of 20 degrees Celsius. Okay, so that would be our rho naught value. All right, so rho naught. Don't worry, we don't need the whole page of this one. It's just the last example. 2.12 times 10 to the negative 8 omega m, right? Ohmmeters. Good, okay? All right, and if this metal is used to make a wire that carries a current of 3.4 amps when manufactured at a circular diameter of 34.8 micrometers and attached to a 5.5 volt, so I'll cross out that superfluous 1 there. I shouldn't say 15, it should just say 5.5. Clean up a little bit, okay? So a 5.5 volt source, then what would be the new current through the wire if the metal was heated up to 50 degrees Celsius while attached to the same voltage source, okay? So the idea here is we're going to go ahead and find out what the current is, okay? Well, I guess we have the current, but we're going to go ahead and find out, I believe it's the length, all right? I think it's the one thing that we don't know. Let's go ahead, let's brainstorm here, okay? So we have, what do we know? Okay, so we've got that the resistance, all right, so volts per current, okay, and we also have that the resistance is going to be resistivity, and then times length over A, all right, good, okay, and so then we can go ahead, and this is rho naught, because it's our baseline one, and so we can go ahead and set that equal to each other, and then find L. Let's go ahead and do that. Okay. So I'm just going to say, okay, well, in that case, I know that volts over current is going to be room temperature resistivity times length over A. Okay. And then I'm going to go ahead and solve for the length because it's really the one quantity we don't know. All right. And so that's going to be my volts times cross-sectional area divided by I times room temperature resistivity, okay? And I'm being very free of space here since we do have the whole page. And so then the length here then would be our 5.5 volts, okay? And then times circular, so pi, all right, we have a diameter, so it'll be 1/2 of the radius we're given, 34.8 times 10 to the negative 6 meters squared, okay? So that's the V times A. I, we know to be 3.4 amps. Okay, and then I'm going to multiply that by 2.12 times 10 to the negative 8 ohm meters times 10 to the negative 8 ohm meters. Okay, so let's go ahead and calculate these numbers. See what we get. Okay, so numerator 5.5 times pi times 0.5 or 1/2 times 34.8 times 10 to the negative 6. Square that. Close off my numerator. Other than squaring, order operations that matter in the numerator because it's all multiplication. But then 3.4, and then times the resistivity, 2.12 times 10 to the negative 8. Okay, so we get a length of 7.26 centimeters, or 0.0726 meters. Okay, now let's look what happens. Now we're going to raise the temperature to 50 degrees Celsius with this temperature coefficient. Okay, alpha equals 2.1 times 10 to the negative 3 inverse kelvins. Okay, so that means, and then when that happens, we're just going to find the new current, I believe. All right, so then what would be the new current? Okay, all right, so first of all, we need to find the new resistivity at this higher temperature. Okay, so then we'll use the resistivity formula. And this one is not a direct, so I'm going to say and, kind of as a side note here. Okay, so and our temperature-dependent resistivity be rho naught. Okay, and then we got to use the formula, so brackets here to be proper. 1 plus alpha times T minus T naught. Okay, all right, so we'll plug in. All right, so then we have our 2.12 times 10 to the negative 8 ohm meters times 1 plus 2.1 times 10 to the negative 3, so 2.1 times 10 to the negative 3 inverse Kelvin, and then we have our temperature difference. We started at 20, we ended at 50, so it's positive 30, so I'm just going to write this as 30 Kelvin. because that's just 50 minus 20, and a degree change in Celsius is the same as 1 Kelvin change. Okay? Okay, so that will give us our new resistivity. We'll go ahead and find that. 2.12 times 10 to the negative 8. 1 plus 2.1 times 10 to the negative 3 times 30. Okay, so 2.25. Never changed that much. We're not looking for dramatic changes here. 2.25 times 10 to the negative 8 ohm meters. Okay, definitely appreciable difference. So it's gone up. Okay, and now we just need to find the new voltage with the new resistance for that new resistivity. Now it's still the same wire. It's this in terms of its length and cross-sectional area. The only thing that's happened is it has a change in its resistivity. Now we could have included thermal expansion as well, because technically things get longer. Right, that's certainly something you could add to this problem, but it will be rather subtle. Okay, so then we'll go ahead and find the new resistance. Okay, it's L over A. Okay, 2.25 times 10 to the negative 8 ohm meters, something we calculated. Then the length that we calculated, we're using a lot of calculated quantities here, 0.726 meters. And then our cross-sectional area, all right, which is this business, 1/2 34.8 times 10 to the negative 6 meters squared. Okay, clean this up. All right, let's go ahead and calculate this resistance. Okay, if I can get it worked out. There we go. I'm going to type this onto my calculator. You can do the same. Okay, follow along at home. Okay, I'm taking saved values rather than rounding. Okay, and then we'll multiply by that length. And then pi r squared. Okay, so 1.72 in ohms is the resistance. Okay, so then finally the current is going to be, okay, just going up to Ohm's law. It's just going to be V over R. Okay, and so it's the same voltage source that hasn't changed. So 5.5. But then divided by 1.72 ohms, which would be more than we would have found if we calculated the resistance to begin with, right? If we'd fed this length back in to find the resistance at room temperature. But let's see, 5.5 and divided by our increased warm resistance, and I get 3.20 to round. So 3.20 is our current when it used to be 3.40. So we had about a 1/5 of a amperage decrease in current, okay, because the resistance went up. Hot things make the current harder to flow. There's just more, because at that point the atoms, the lattice, as it's called, of the atomic nuclei start shaking around more, causing more collisions with those wayward electrons. Okay, so rounding to 3 sig figs, 3.20 amps. Done. Okay, so that one involved a few more steps, but even then, the equations, definitely followed naturally from one another. Okay, all right. Well, thank you so much for watching this lecture. There are, of course, extra practice problems for you to do. I hope this introduction to resistance and resistivity has been straightforward mathematically, but has been very informative and part of the bigger picture of electricity and circuits. All right, bye for now.